Okay, now let's start with the Albite Anorthite solid solution system or the Plagioclase system. Okay, so this one we will talk about. This one we will talk about. So introduction, Albite and Anorthite are part of the Plagioclase solid solution. Remember, this is a Plagioclase complete solid solution series. It involves coupled substitution of SiNa with CaAl, Albite NaAlSi₃O₈ and Anorthite CaAl₂Si₂O₈. Okay, so pure Albite melts at 1118 degrees Celsius and pure Anorthite melts at 1500 degrees Celsius. Pure anorthite, remember, pure anorthite and pure albite, that is, pure anorthite is at this temperature, this composition will melt at this temperature, and pure albite will melt at this temperature, 1118 and 1500 degrees Celsius. Here 1500 degree Celsius. So Plagioclase melts between the melting point of its end members, that is this 118 degrees Celsius and anorthite 1500 degrees Celsius. So Plagioclase, that is the middle members, can melt at any of the given point, between the any of the given point, given temperatures. Intermediate compositions like Albite 50 and Anorthite 50 melt over a temperature range of 1220 degrees Celsius to 1410 degrees Celsius. Okay. Intermediate temperature of, say, this one, this composition, right? Above the liquidus is all liquid. We know that above the liquidus is all liquid. Below the solidus is all solid. Between them, this liquid plus crystal coexist. So above the liquidus is the liquidus curve. All things are solid. All things are melt. That means liquid in this phase having what? Having one phase is there, but two components are there, right? One phase is there, two components are there. Whereas below the solidus, again, one phase is there, that is only solid will be here, only solid will be here in this phase, and again two components are there. So you can get the degree of freedom out of it. So initial condition, melt composition is 36% anorthite and 64% albite. Say we take a composition A, we take a melt A, listen carefully from here, we take a melt A of said composition, say anorthite 36% and its complement albite of 64%. Okay, here. Now what will happen? Crystallization. Say we are giving isobaric phase diagram. Isobaric means the pressure will remain same. This the pressure will remain same, and we are just reducing. We are just, this is the what? This is the T degree Celsius Tx curve. This is also called a Tx curve, where we are taking a single pressure. We are not changing the pressure, but we can change the temperature as well as the weight percentage of anorthite and albite. But here the pressure is constant. So this is a isobaric phase diagram. That means a phase diagram consists of temperature and weight percentage where the pressure is constant. Okay. So at point A, say this is the point A at 36% anorthite and its complement. At point A, at pressure corresponding to point A, bulk composition of 36% anorthite, we have only the liquid phase. We have this on. We have this phase only, right? So phase, that is phi equals to 1, component equals to equals to 2. So F equals to C minus phi plus 1, that is 2 minus 1 plus 1, that is 2. So degree of freedom here is 2. That means the weight percentage as well as the temperature is independent of each other. Okay, we can vary in anything in this phase. Now at point B, where the first crystal will start, we'll start having the first crystal from the point B. Okay, from the point B we'll start having the first crystal. So at point B, that begins at 1402 degrees Celsius. That begins at 1402 degrees Celsius. At this temperature, the liquidus is intersected. Okay, the first A composition hits the liquidus and we'll start having the first crystal out of our melt. The first plagioclase crystals to form is this one, right? C. The first, so we will just at this point we'll just draw a horizontal line that connects with the solidus, and then we'll project it to the weight percentage, and we are what we are having is 71% anorthite and its complements, that is 29% albite. So we are getting 29% albite and 71% anorthite out of our melt. The first crystal that will crystallize is C of C composition, this composition, excuse me, of C composition. Now let's say again it gets cooled, then it will come to D, right? It will come to D. So here at this point, since we are just starting to get our crystals, so here it will be 100% melt. How we are getting it? We are calling it the lever rule. The lever rule. By the lever rule, we will understand how much percentage is our melt and how much percentage is our crystals that are being formed. So here it will be 100% melt. Okay. Now here we are getting two phases, right? We are getting liquid phase as well as the solid plus liquid phase, right? This is another phase. So we have two phases. So phi will be 2, component is 2 again, this is constant. F equals to 2 minus 2 plus 1, that is 1. That means at this line, I have remember I have told you before also that at any line we will get a degree of freedom that is equals to 1. So we can either change the temperature or we can change the weight percentage, and if we change any one, then the other one will automatically be fixed. Say at this, if we are keeping the temperature at D, then automatically its weight percentage will be fixed. Okay, so they are dependent on each other. Now say at any point E, how do we calculate? Say this again cools down and comes to D. Okay, this will follow this path only. This will follow this path. The melt will follow after hitting the liquidus, will follow this path. It will come to D, then come to G, like that. So say it will comes to D. Okay, now the crystal that it will form at D will be, if we have to draw a horizontal line with touching the solidus, right? This F. So now the F, we draw a vertical line touching the weight percentage, and wherever it hits it will give that composition. Okay? Wherever it hits it will give that composition of albite and anorthite. Now how do we get how much melt it is producing and how much crystal it is producing? So we have to draw a vertical line from our initial melt that touched the liquidus. Okay, this is the vertical line of our initial melt, and wherever it bisects the this horizontal line, we just have to calculate the length of this line, and we will get, say this is 66% of the melt is here and 34% of the crystal it has already formed. So rock composition of D will give, will have if when the melt reaches the D point, it will be having 66% of melt and 34% of crystals. Okay, this is what it is. This is called a lever rule. At any point E, the relative proportion of solid and liquid can be calculated using the lever rule, that is liquid by solid, EF by DE, that is EF by DE, that is the ratio. So we get this using lever rule. So the crystallization path will be CFH. CFH is the crystallization path, whereas the melting path is BDG. As temperature decreases, albite rich plagioclase progressively crystallizes. So as we see here, we are getting 71% of anorthite. Here we are getting less anorthite and more albite. Okay. So as we progress, we will get more albite and lesser anorthite. So here what is it is saying? It is saying as temperature decreases, albite rich plagioclase progressively it crystallizes. Plagioclase and melt compositions evolved continuously along the liquidus and solidus curve. So plagioclase and melt compositions evolve continuously along the liquidus and solidus curve. Crystallization continues until 1 to 16 degrees Celsius, solidus liquidus temperature point G. So it will go maximum up to point G, because at point G, if we just plot it here up to H, we will see that it is 100% crystal. Here it has 100% melt. It is at the left of this fulcrum, right? Left of the fulcrum. So it is 100% melt. This is 100% crystal. Sorry, 100% melt. This is 100% crystal. So all crystals has been crystallized from the melt. So no melt is there for further cooling. That means it will stop here and then it will crystal. Remember, this H is of the same composition of the initial melt A. Okay, I think you understood this. How we are getting the last mineral to crystallize having the same composition of the initial melt, that is A. Okay, so crystallization will stop at H. Crystallization continues until 1 to 16 degrees Celsius, 1 to 16 degrees Celsius. That is the solidus liquidus temperature at point G. Final solidification at point G, the same temperature. At 1 to 16 degrees Celsius, the last drop of melt has a composition of anorthite 7, remember, and albite 93. So, see how we are getting different composition of crystals. First, we got crystals of anorthite 71, and at last, we got crystals of anorthite 7% only, whereas 93% of albite we are getting the last crystal composition at. So below this temperature, only solid plagioclase remains. All liquid is consumed. So under equilibrium, the final plagioclase composition is this one. The last crystal, this is actually the composition of melt. Okay, this is the composition of melt, and this is the composition of the crystal, last crystal to form. So the melt will be having, last drop of melt will have 7% anorthite and 93% albite. Okay, last drop of melt will have 93% albite and 7% anorthite, whereas the last crystal to form will be of composition H, that is 36% anorthite and 64% albite, that is similar to that of the initial or the starting melt composition. So phase is F equals to 2 minus 1 plus 1, that is 2, varies for the same composition as the solid cools to point D. Oh, sorry, this is not the one. Where were we? We were, yes, 2. T varies with the same composition as solid cools to D. Point D. Okay. Equilibrium. So solid 1 plus solid 1 gives solid 2 plus solid 2. This is equilibrium crystallization. Okay. Solid 1 and liquid 1 will give solid 2 plus liquid 2. No separation of melt or crystal is happening here. The crystals remain suspended in the melt, and cooling and crystallization are slow enough to allow continuous and complete reaction between crystal and melt. So slow cooling results in equilibrium crystallization, where the we are allowing the crystal to get reacted with the melt. Okay. So the early formed crystals will, on cooling, react with the melt continuously and thereby gradually change their composition along the solidus from B to F. Along the solidus from B uh, B to F, we will have the simultaneous liquid changes from A to E. Okay. A to E. Okay. The liquid changes from A to E. In such circumstances, the crystal will not change composition beyond F, and the end product is a homogeneous mixed crystal having the same composition as the initial melt, that is An36, Ab36. This is in case of an equilibrium melting. Remember, this is the case of equilibrium melting where we are not separating out the melt or the crystal. Now let's come to crystal fractionation. What will happen if we are separating out the crystal from the melt and we're not allowing the melt to react with the crystal? So if crystals are continuously removed without reacting, the melt evolves along the liquidus curve towards sodic feldspar. So it will evolve into sodic feldspar to evolve, or it will go towards sodic feldspar, producing increasingly sodic crystals until only a small amount of pure albite remains. The final solid will be pure albite. So final solid will be pure albite. Here it will come to this point. This point. If we are removing our crystal from the melt, then the final crystal that will form will be of pure albite condition. We cannot define it using this curve because we are continuously removing the crystal, and then a new bulk composition of melt will be prepared. Say this is the initial melt, it hits and then crystal forms and we separate out, then again goes here, and then we again separate out. So this will be the new bulk composition, right? Then because only melt is there, we are separating out all the crystals from it. Again it goes here, then again we are separating out. That means a new bulk composition of the melt will be prepared. So we are not allowing it to crystallize with the already formed crystals. So final solid will be pure albite. Here comes zoning. Now comes zoning. So before going to zoning, let me just give you a brief study of this crystal fractionation. So what happens is this purely fractional crystallization involves the physical separation of solid from the melt as soon as it forms. So we know that if we remove the plagioclase crystal as they form, which can happen by making them sink or float like that. So the melt can actually no longer react with the crystal. The melt actually composition continues to vary along the liquidus as new plagioclase crystallizes along the solidus. Okay, so the melt composition continues to vary along the liquidus as new plagioclase crystallization uh, along the solidus. Because the crystals are being removed from the system, however, the melt composition continuously becomes the new bulk composition. I've just said the melt composition continuously becomes the new bulk composition, thus shifting inexorably towards albite. So it will shift towards the albite. As a result, the composition of both the final liquid and the solids that form, it will be albitic than for that, which is not similar to the equilibrium crystallization, right? And it will approach pure albite in efficiently fractional system. So last crystal that will form in a fractional crystallization will be a pure albite. So fractional crystallization implies that a range of magma types could be created from a single parent magma by removing varying amounts of crystals that are formed in a magma chamber. I hope you understand what fractional crystallization is.